Welcome to Calculus. Today we will investigate finding second derivatives of trigonometric functions, focusing on applying the 6 differentiating rules for sine, cosine, tangent, cotangent, secant, and cosecant, as well as applying the product rule. Let's take a look at our first example. So we'll look at 3 total examples, beginning with a simple function. So here we're looking at our function y equals sine of x. And our instructions are to find y double prime, or the second derivative of y. So the way to go about that is, first of all, to find the first derivative. So I'm going to find the derivative of y, which is going to be the derivative of sine. So I see in my table that I've recorded here the derivative of sine, d dx sine x, is cosine x. So that's pretty immediate. I then want to find the second derivative. So again, once I take the first derivative, to find the second derivative, I just apply the differentiation rules to the first derivative. So now I'm looking for the derivative of cosine x. And I see that that is going to be, according to my table, negative sine of x. So surprisingly, when I take a second derivative of sine of x, it really comes back to the negative version of itself. So a fairly simple example there to begin. Let's take a look at one that involves a product. So our rule here is y equals e to the power of x times cosine x. So again, my instructions are to find y double prime, the second derivative of y. And because I've got a product here, what I see is that I have need of the product rule. So remember, product rule says that if I've got a function big F of x that equals some small f of x times some small g of x, I could say that the derivative of big F of x has this pattern. The derivative of big F of x is the original small f of x times the derivative of g of x plus original function small g of x times the derivative of little f of x. That's that pattern that we've grown accustomed to using for the product of two functions where I'm finding the derivative. So you can see the need to find what is small f of x. So for us, that's that first factor, e to the power of x. So my derivative of small f, remember that special function, e to the power of x, is its own derivative. Now for cosine of x, I'm going to identify that as small g of x, my second factor in the product. So the derivative of small g is going to be equal to, from my table, negative sine of x. So I'm ready to fill in here and to calculate the first derivative of y. So that's going to be for us again, e to the power of x, that's my original f of x, times the derivative of g, which is negative sine of x, plus original g, which is cosine of x, times e to the power of x, the derivative of f. I'm going to write that in a factored form for my first derivative. I see each of these has e to the power of x, so that's going to be e to the power of x times, and I'll put the cosine first, so cosine x, since the sign is minus, I'll put that second. So that one, we've reached the first derivative. Now we want to take the second derivative. Same way, it's the same concept. Once I have the first derivative, to get to the second derivative, I just take derivative of the first one. So to get y double prime, again, I have need of the product rule. Because again, I've got e to the x times, we can treat this cosine x minus sine of x as our little g of x. So I'm going to reapply product rule to find the second derivative. And I'll just kind of do the same thing. So these are different in terms of what they're representing, but I'm using that same f of x, g of x, f prime of x, g prime of x. So again, I have that factor e to the power of x, so its derivative is itself. And then to take the derivative of g of x here, I've got a sum. So the derivative of cosine x negative sine of x minus the derivative of sine of x is positive cosine x. So now I see that that has both of them negative. So again, I'm going to reapply product rule for this second derivative. Let's set it up. So this is y double prime. And just to remember how that goes, it's the original f of x, so e to the power of x, times the derivative of g, so that's negative sine x minus cosine x, plus original g of x, so that's my cosine x minus sine of x, times e to the power of x. And then we should look and see if we've got any possible cancellations there. So I'm going to, again, focus on factoring out this e to the power of x. And then what's left is going to be these four terms. So it's negative sine of x minus cosine of x plus cosine of x minus sine of x. As I finish writing, see if you can locate any cancellations in that green sum. I see that the sine values won't cancel because they're both negative, but my cosine, one negative, one positive, will cancel. And so what I'll get here is, we'll draw a division, or kind of just a separation line there. Y double prime, or second derivative of y, is e to the power of x times negative 2 sine of x. And that completes that second derivative for that second example. So definitely we had to apply the product rule there. Let's take a look at one last example that involves secant and tangent. So here I've got my function y equals a, and I'm going to assume that a and the b on tangent are numerical coefficients. We'll treat this as constant coefficients. So y equals a secant theta plus b tangent theta. Let's apply our process here. So for the first derivative, I'm going to apply my constant coefficient rule, that a stays in place. Derivative of secant theta is going to be secant theta times tangent theta. Remember that theta is just a description of the independent variable, which in this case could be x or theta. It's describing an angle measurement. Plus, I'm going to scoot around here to this second line, b, and then the derivative of tangent, which is secant squared of theta. And that gives me really my first derivative. That's good as is. So then I want to apply second derivative. So I'll take the derivative of my first derivative to get y double prime. But what I've got really is a set of two products. So I'm going to actually make some room here. I'm going to call this b times secant squared of theta. And I do that because I need to write underneath both of these, because it looks like to find my second derivative, I got to apply my product rule in two spots. So in fact, I'm going to get rid of that y double prime for now, just to make sure we got enough room here. So for our first term here, so a secant theta tangent theta, I need to call my f of x here, small f of x, secant of theta. In fact, that's small f of theta. So the derivative of f of theta, because I'm going to use the product rule here, is going to be the derivative of secant, so that's secant theta tangent theta. And then for my second part there, I'll identify small g of theta as tangent theta, which means the derivative of g at theta is going to be secant squared theta. So let's take the derivative of that first term. Again, what we're building is y double prime. So again, we'll set up for the derivative of that first term, a secant theta tangent theta. So the a, again, is just going to stay in place. And then I'm going to pick up with my product rule pattern. So f at theta is secant theta times g prime at theta, that's secant squared theta. And that's plus the derivative of g. Actually, let's record that as the original of g. Make sure I get the correct pattern. So that's tangent theta. And this is the derivative of f. So times secant theta tangent theta. And that finishes the derivative, at least in an unsimplified form, of that first term. So now I have to take my attention to this second term. We'll circle it here in some light blue. So that's b secant squared theta. So again, I need to treat that also as a product of b times secant theta times secant theta. And I'm going to apply the product rule again, but in a way to the second term here. So my f at theta for this second term, and I'm trying to separate it over here and do the scratch work over here on the right. So it's kind of weird because both of the pieces are the same, but I do have two of them. So the first one we'll identify as f of theta. So the derivative of small f is going to be that same secant theta tangent theta. And then separately, g of theta is the same. G of theta is the second occurrence of that factor of secant theta. So its derivative is also going to be secant theta tangent theta. So for my second term's differentiation, I'm going to write plus b. And then for my parts, using the product rule pattern again, so secant theta times the derivative of g, which is secant theta tangent theta, plus secant theta is also the original small g, and then derivative of small f over here is secant theta tangent theta. So again, no surprises, those are identical terms there. And so as I face this now to simplify, I want to think, okay, how can I simplify this in a way that will be good to record? This first term, so let's focus here on the a coefficient one. It's going to be a times, I've got secant theta times secant squared theta, so that's secant cubed of theta plus secant theta tangent squared of theta. So that simplifies that first differentiation, that first term there. For the second term, plus b. And here I've got secant squared of theta tangent theta, but I've got two of them and they're identical. So I'm going to bring that 2 out front with the b, and that really completes our second derivative. So second derivative of y here is A times quantity secant cubed theta plus secant theta tangent squared theta plus 2B times quantity secant squared theta tangent theta. Well, thank you for joining for this investigation of taking the second derivative of trigonometric functions. I'll let you go take second derivative of your own trig functions. Thanks for joining. See you soon.